Let's get to our example now where we find the electric field of a ring of charge. So we have a thin ring. Remember, we said these problems were one-dimensional, so with length but no thickness. Our ring has a radius A, and the total amount of charge is Q, and it's uniformly distributed along the ring. That means we don't have areas where the charge is bunched up. It's all evenly spread out. If we look at the picture, we see all these plus signs. That tells us that the charge is positive. We're asked to find the electric field. Remember, that's a vector. We need magnitude and direction at some point x along the axis of the ring. So the axis of the ring is a line that comes out from the center. And it's perpendicular to the plane of the ring. As we get into these problems, we have to draw in 3 dimensions quite a bit, so it's good to explain what we're doing. So we're going to choose a point P, and point P is some distance x from the center. We'll put on our coordinate system. We'll take x to the right. We'll take y up and down. So in our picture here, y comes up and down. And z is the coordinate that comes, oops, that one is y. Z is a coordinate that comes out of the page. So z comes out like this, and negative z goes into the page like this. Okay, so our goal is to find the electric field here. First, let's use symmetry, and we'll sort out the direction. Then we'll go ahead with the calculation.
Let's use a physical model to evaluate the symmetry when finding the electric field on the axis due to a ring of charge. Okay, so our model involves a hula hoop. That's our ring of charge. We need the axis of the ring, so that's going to be represented by my meter stick. If I turn it sideways, you can see it a little better. So the axis just sticks out perpendicular from the center. Okay, let's think about the symmetry. First, I'm going to ask what happens due to a bit of charge. So my hand is the dq. What happens? What's the direction of the electric field made by that bit of charge? So the direction of the electric field points partly down and partly out towards you. Let's see if I turn it sideways. Is that even a little bit more clear? So the direction of electric field is partly down and partly out towards you. Okay, I think you should be able to see that there now. Partly down, partly out towards you. That's what happens to a DQ on the top. What about for a DQ on the bottom? I move my hand to the bottom. The electric field now points partly up and partly out. So every bit of charge from the top half of the ring will have an electric field that points partly down and partly out. All right, so that takes care of the top and bottom. So everything on the top will have a bit of field that points down. Everything on the bottom will have a bit of field that points up. So the up and down components cancel. What about the left and right components? So let's take a DQ on this side of the ring. The electric field points partly away from me and partly forwards. So that's what happens on this side. If I come to the other side of the ring, getting a little tangled now. The electric field again points away and partly out. So here the electric field from the right side of the ring points left. The electric field from the left side of the ring points right. So the left and right parts cancel, but there's still some field that points out towards you. So all of the up and down parts cancel. All of the left and right parts cancel. The net of electric field that's left over is the parts of the field that point out towards you. So that's the direction of the electric field due to a ring of charge. It's away from the ring of charge along the axis.
Okay, let's just quickly write that down in a summary before we get into the math. So in our coordinate system, x was the axis, that was the one pointing out. Y is up and down, and z is in and out this way. So the up and down components canceled. So EY is the integral of each DEY. That was 0. EZ, that was the left and right parts in my picture. It's the sum of the Z parts. They all go to 0. X, the part that's along the axis, the part that was sticking out towards you in the video, they don't cancel. And then all together, when we find our answer, the total electric field will be the part that didn't cancel, the x part, in the x direction. Let's now carefully go through the process of finding the electric field of our thin ring of charge at point P. Our first step in the process is to identify an element of charge dq. So draw dq. That means pick some little bit of the ring, shade it in, and label it dq. That dq is a positive element of charge, so it's going to make a little bit of electric field at point P. The little bit of electric field is going to point away from dq. And this is what we were modeling with the hula hoop and the meter sticks. If you have trouble visualizing this, then by all means, grab a roll of masking tape and maybe make a vector out of a toothpick and see if you can model this at home. So we want to draw dq. We want to draw dE, the element of electric field made by dq, and we want to draw the components of dE. So we know that dE points away from dq. That helps us identify the components. So the x component is away from the ring. That's in the positive x direction, dEx. Our dq is on the top half of the ring, so the y component points down. And our dq we picked was on the back half of the ring, so the z component points outward or in the positive z direction. Okay, next we can identify some symmetry. And this is what we did with the hula hoop and the vectors. We know that every bit dq on the top half of the ring makes an electric field that has a component that points down. Every bit of dq on the bottom half of the ring would make an electric field that has a component that points up. The y components cancel. That means that EY, which is the sum of all the y components, equals 0. Likewise for the z components, everything on the back half has a z component that points in positive z. Everything on the front half has a z component that points towards the back half. So those positives cancel with those negatives, so the z components cancel. And that leaves us with the x component. So the x component is the part that we want to calculate. And we don't have to, but we can write down that the x component is the sum of the total x component is the sum of the individual x components, or the integral, because the integral means the sum, and that guy is not going to be 0. Okay, the next step in our process is how do we even calculate what those components are? Well, this goes back to our regular trigonometry. We know that to find components, we use sine and cosine. So let's identify an angle. I'm going to call this angle theta, which makes this angle theta. So I see that my DEX is adjacent to my angle theta. That means I can use cosine to find my DEX. So DEX is equal to DE times cosine theta. So that's just finding a vector component. Here's where we start to really get into the new stuff. So now we have to ask, what is dE? What do we fill in for dE? Well, remember, electric field is Coulomb's constant K times the charge divided by the distance squared. So our dE then is equal to Coulomb's constant K times our charge. Our charge is our charge element dq, divided by our distance. We better label this distance on the diagram. Distance is the distance between our charge and our point, r. So now that I've labeled r in my diagram, I can put r in my equation, times cosine theta. Okay, now what can I do about this? DEX equals all this stuff. Can I say anything about cosine theta? Let's come over onto the side. We might remember from high school geometry, hopefully we remember, that cosine theta is adjacent over hypotenuse. And if we look at this triangle, do we know what the adjacent and the hypotenuse are? Well, the adjacent is the distance x in the x direction because we said we were finding the electric field at some distance x. So the adjacent is x, and our hypotenuse is r. So our cosine theta, which is adjacent over hypotenuse, is x over r. Let's fill that in for our next step. So I've got k times dq over r squared times x over r, which gives me k times dq times x over r cubed. Feels like we could make this a little bit simpler. Do we know what r is, or can we figure out what r is? Well, r goes from dq to our point P, so r is connected to a point on the ring. The distance from the ring to the center of the ring, that's just the radius of the ring. That's that radius A that was given. So if we look at this triangle, this is a hypotenuse, x is one leg, and A is the other leg. So r is a hypotenuse of a right-angled triangle, so r squared is equal to a squared plus x squared. Let's get that written down. That means that r is equal to a squared plus x squared. Take the square root, or an exponent of 1/2. Now in our equation, we have r cubed, so let's cube our expression for r. Okay, so there's an expression for r cubed. Let's fill that in for our last step here for our dEx. So remember, what we're finding here now is the x component of the element of electric field. We haven't found our total electric field yet because all we know so far is dEx. To get our total electric field, we're going to have to do the integral. We're going to have to do that sum. So we've got k times dq times x. Put in an expression we just found for r cubed, which is a squared plus x squared to the 3 over 2. All right, so that much is done. Next slide, we'll go on to do that integral and find our answer. We'll keep going now. To find the total x component of electric field, what we have to do is add up all of the elements of the x component. So we have to add up all the little x components. That'll give us the total x component. Of course, when we have these continuous charge distributions, to add or to sum means to do the integral. So let's fill in our expression for dEx. Well, in fact, why don't we just even write in that step? So our total x component is the integral of our individual x components equals the integral of k times dq times x over a squared plus x squared to the 3 over 2. Now, here's why the ring example is my favorite example of these continuous charge distributions. Our next step in integrating is that we can take our constants out front. So let's look at all our symbols and let's ask what's constant. How about K? Well, K is Coulomb's constant, 8.99 times 10 to the 9. That's a constant. It can come out front. How about X? Well, X is the distance between our point P and the center of the ring. That's this distance here. That doesn't change in this problem. So, yep, X can come out front too. How about A? Because down here in the denominator, X and A are coupled. Well, A is the radius of the ring. That's a constant. So a squared plus x squared, that's also constant. So this whole denominator can come out front. Okay, let's see what that looks like. We've got k times x over a squared plus x squared to the 3 over 2 times the integral of dq. Okay, last step. Here's where I think the math is really lovely. What does the integral of dq even mean? If you had this question in math class and your math prof asked you what's the integral of dx, you'd probably just answer x. But what's the physical meaning? Well, the integral of dq, the integral part means add, dq means each element of charge. So this means the sum of every little bit of charge on the ring. So this bit plus this bit plus this bit all the way around the ring, we add together every little bit of charge. What would we get if we added together all those little bits of charge? Well, what we'd get would be the total charge. So this is equal to the total charge, Q. That's where I think the math is pretty nifty. So this tells us now in our final step that our x component of electric field is K times X times Q over A squared plus X squared to the 3 over 2. We're not quite finished because electric field is a vector and we do have to write it as a vector. So it's going to be our X component next to an I hat. Our Y and Z components are 0, so we don't need to write those in. So that's the electric field due to our ring. One last thing we could do is draw the electric field on our picture. So we found the electric field at point P, and that was pointing directly away from the ring. If we found the electric field at a point P on the left side of the ring, that would still point away from it. I don't have quite enough room to draw the full-on vector there, but that's what it looks like. There are some other questions we might ask, and I think why don't we just go through a few of them. So part A, let's plot the magnitude of the field as a function of x. There's some different ways to do this. You can look at the form and you can know what the form of the graph would look like. You can plug in values and just do a connect the dot graph. I kind of did it that way, but I used an Excel spreadsheet. So I used an Excel spreadsheet to do a connect the dots graph. So the line going up through the center, that's the magnitude of the electric field. The horizontal line, so the middle spot is x equals 0. That's dead center of the ring. You'll see that the electric field is equal to 0 there. That's another one of our questions. And then the horizontal line is the value of x, the distance from the ring. This is kind of a neat shape, actually. So our ring, it has 0 at the center, comes up pretty steeply to some value, and then dies away. And then it looks exactly the same on the other side. The only difference on the other side is that the electric field points in the opposite direction. So an interesting question, and that's one of the questions in my list, is where does this maximum happen? So what's going on there? How big is the field right there? That's interesting. And then also kind of what happens when we're far away and what happens at the center. So let's look at some of those questions. So question B, what is the electric field at the center of the ring? So at the center of the ring is x equals 0. So our electric field is K times 0 times Q over A squared plus 0 squared to the 3 over 2 equals 0. So our electric field is 0 at the center of the ring, and that was something we had already seen due to symmetry. Our third question, part C, is a little bit of a Jedi problem. We're going to have to roll in some things you know from math class, but I don't think it's too hard. Where is the electric field the maximum? We could definitely pick it out on our graph. And what we know at a maximum is that the slope is equal to 0. So that's where the derivative of e with respect to x is equal to 0. So what we'll do is we'll take the derivative of e with respect to x, we'll find that expression, we'll set that equal to 0. So to get started, we're going to do d by dx of k times x times q over a squared plus x squared to the 3 over 2. Can take our k and our q outside. We're left with d by dx of x over a squared plus x squared to the 3 over 2. Now, lots of you fresh from math 1,000 would probably go ahead and do the quotient rule. For the life of me, I can't remember the quotient rule, but I always remember the product rule. So I'm just going to write this guy as a product. Got d by dx of x, that's our numerator, and our denominator, a squared plus x squared to the plus 3 over 2, could be written as a squared plus x squared to the minus 3 over 2. That's how I can write that as a product. Okay, I'll go ahead and apply my product rule. And what I do is k times q. So you take the derivative of the first guy, derivative of x, that's 1, multiply it by the second guy, a squared plus x squared to the minus 3 over 2. Then you take the first guy, x, and multiply it by the derivative of the second guy, which is minus 3 over 2 to times a squared plus x squared minus 3 over 2 minus 1 is minus 5 over 2. Multiply that by 2x, finishing your chain rule. I'm assuming you guys are really comfortable with derivatives and you know how to get this one done. Okay, so what do we have next? So I've got kq outside. I think I'll go back to writing these guys as fractions. 1 over a squared plus x squared to the 3 over 2. Over here on this side, I've got a 2 here and a 2 here. They cancel. So I've got a minus 3 in front. I've got an x times an x to give me an x squared. And in the denominator, I've got a squared plus x squared to the 5 over 2. I'll get a common denominator by multiplying this term by a squared plus x squared. kq a squared plus x squared. Do that on top and bottom, so now my denominator is a squared plus x squared to the 5 over 2 minus 3x squared over a squared plus x squared to the 5 over 2. This will simplify one more bit, so now that I've got a common denominator, I'm going to have a squared plus x squared minus 3x squared all over a squared plus x squared to the 5 over 2. I think I'll write that on the next slide. Let's keep going with the expression now. So that's k times q, a squared plus x squared minus 3x squared all over a squared plus x squared to the 5 over 2. So that's k times q times a squared minus 2x squared over a squared plus x squared to the 5 over 2. Okay, that's about as simple as I can go. You might be able to do a little bit better. And what we know, to get a maximum, that has to be equal to 0. So let's set that equal to 0 and see where we get. So dE by dx, which is equal to k times q times a squared minus 2x squared over a squared plus x squared to the 5 over 2 equals 0. We can divide both sides by kq, a squared minus 2x squared over a squared plus x squared to the 5 over 2 equals 0. So if my numerator is equal to 0, then the whole expression is equal to 0. So a squared minus 2x squared equal to 0 will give us our result. That means that x is going to be a divided by root 2, and it can be plus or minus. It can be in front of the ring or behind the ring. So this is the position at which the electric field is a maximum. Part C also asked us to find the value of the electric field at this point. I think I'm not going to go ahead and put the numbers in. I'll leave you to do that algebra. It's probably pretty boring to watch me do it. So what is E at that point? What you do is you plug in plus or minus a over root 2 in your expression for E, and what you should get is E is equal to 2 times k times q divided by root 27 times a squared in the x direction. So it would point away from the ring. Last bit of the question to look like is, what is the field if our distance x is a lot bigger than the radius of the ring? So what if we're pretty far away, but we're not infinitely far away? That's what part D is asking. So what is E when x is much bigger than a? Well, we'll write down the expression for the electric field, kxq over a squared plus x squared to the 3 over 2 I hat. Now, what does it mean that x is much bigger than a? So if x is an awful lot bigger than a, then a squared plus x squared. So if x is already big, then x squared is really, really big, especially compared to this a squared. So that means a squared plus x squared is about equal to x squared. The a squared part just doesn't matter very much. So let's fill that in for our expression for x. Oh, I used the wrong color. Switch back to black. K times x, so this is an approximate term now, x over x squared to the power of 3 over 2 I hat. That's equal to k times x over q. X squared to the 3 over 2 is x cubed I hat, which is k. X over x cubed gives us an x squared in the bottom. X squared times I hat. It's like a point charge. So once you get really far away from that ring, it acts and looks just like a point charge. And then as you go x equals infinity, as you get super duper far away, the electric field goes to 0.